you just witnessed was a series of steps taken in order to launch our model cannon.
Now, what separates our model cannon from any other average Joe's model cannon is not the materials we use or the methanol we bought from the hardware store. It's the ingenuity, the heart, the spirit that was put into building this masterpiece creation, built by the greatest minds alive.
Our cannon is more stable, predictable, and reliable than any other cannon on the market. The first step is heating the cannon. It is necessary to heat the cannon to aid the vaporization of the methanol. Methanol gas will provide a more complete combustion.
The next step in preparing our model is taking the necessary amount of methanol, putting it into the barrel of the cannon. So that the methanol in this bottle and the oxygen in the air will provide a exothermic reaction which produces carbon dioxide, water vapor, and heat energy. Now, this will be the combustion reaction which propels the ball.
Once the methanol is inserted into the cannon, it is necessary to shake the cannon. This forces the methanol to coat the walls of the barrel. This provides a greater surface area for the combustion reaction to occur and therefore makes the launch more efficient.
Finally, we mount the cannon at the appropriate angle and insert the projectile. It is now ready for launch.
The next step in the process is scaling a model-sized cannon up into real life.
To find the diameter we need for the life-size cannon, we'll take the overall measurement of the clown, half it, and that will be used for the diameter. To find the amount of methanol required to launch a clown from a life-size cannon at the same angle and acquire the same distance as the model, we would take the mass of the clown divided by the mass of the ball and find that ratio.
We can use this ratio to find the fuel we need in a large-sized cannon by multiplying it by the fuel used in a small-sized cannon. It's as simple as that, really.
If we divide the displacement of the clown by the amount of methanol required to launch him, we will find the distance acquired per milliliter.
Using this amount and the desired 30 meters, we can find the amount of fuel required in milliliters. The first experimental uncertainty of our project occurred when we were shaking our cannon to spread the methanol within the barrel. See, we simply could not shake the cannon the exact same way every single time, and therefore there will be experimental uncertainty. The second experimental uncertainty we encountered was when heating the cannon. We simply cannot heat the cannon to the same temperature every single launch. And since the temperature of the cannon is responsible for the vaporization of the methanol, and the vaporization of the methanol is responsible for the propulsion of the ball, it's simply going to have a different propulsion every single launch. The third and final experimental uncertainty we encountered came in the form of the insecure bindings, aka duct tape, with which we used to bind the cannon to the mount. This resulted in a shaking of the cannon during the launch.
But don't worry, the first experimental error can be solved by placing a sprinkler-like mechanism inside the life-size cannon. This mechanism will evenly distribute the methanol against the walls of the cannon. The second error, which involves the heating of the cannon, can be solved by heating our life-size cannon to the exact same temperature every time, using heat-sensing technology. The third experimental error, which involves the secureness of the cannon, can be solved in our life-size model by creating a very sturdy mount using concrete and screw fastenings.